Hello, we're going to talk today about the pH scale and introduce some pH calculations. As you remember, the pH scale was invented by the Danish Søren Sørensen. He worked in the brewing industry and he was trying to figure out when the beer was done. Didn't want it to become too bitter and developed the pH scale out of necessity for that reason. The pH scale, as you remember, is a logarithmic scale, and it goes, most textbooks will say 0 to 14 or 1 to 14. To put this in perspective, a 1 molar hydrochloric acid solution would have a pH of 0. Hydrochloric acid can actually be sold as concentrated as 12.1 molar, and we're going to learn that that would actually have a negative pH value. A base of 1 molar sodium hydroxide would correspond to a pH of 14. Some things that you might be familiar with: household ammonia. It tends to be a cleaner that we might use. pH about 12. Blood is going to be between 7.2 and 7.4. Blood's a little bit bitter. If you've ever tasted your own blood, you realize it's just a little bit bitter. We've got vinegar down here at pH 3, lemon juice pH 2.5, and stomach acid around pH 2. Pure water would have a pH of 7.0. And so the pH scale, if we're looking at it, if you have let's try that again here. On the pH scale, if you have a value that is less than 7, that is an acid. If it's greater than 7, it's a base. And we thought about some examples. Our acid example was battery acid. Now that's not hydrochloric, it's sulfuric, but it's nevertheless battery acid. And our base that we think about is Drano, or drain cleaner. Here's some other listing for you. Lots of different things that you can look at. I'll let you kind of look at them and consider them. All right, we can add more: pure water and lemon juice 2.2, ammonia 11, drinking water. Now, drinking water can be acidic, it could be basic. It really depends on what the water is sitting on. It's not going to be the same every time. Here's bleach at pH 12, vinegar 2.8, and so on. So we can see that lots of different things have different pHs. Some people, they enjoy the taste of tomatoes, but tomatoes are very acidic, 4.2. And if you eat too much tomato, that can give you an upset stomach. All right, we'll kind of move on from there. I'm sure you can find charts like this online to figure out the pH of lots of different substances. Now, this one we're going to start to think about using some math related to it. I see I've got a little typo here. The 7 belongs up here. And what it says, what I want you to notice, is that we're looking at the pH numerical value, the hydrogen ion concentration, the hydroxide concentration, that's what brackets mean, concentration, and the pOH. And maybe if you look, you realize there's a pattern here. When the pH is 7, the hydrogen ion concentration is 1 times 10 to the negative 7th. When the pH is 9, the hydrogen ion concentration is 1 times 10 to the negative 9th. When the pH is 2, the hydrogen ion is 1 times 10 to the negative 2nd. So we can sort of think of pH as the power of the hydrogen ion concentration. See, if the hydrogen ion concentration is 1 times 10 to the negative 13th, the power is 13, the pH is 3. Now, we have a similar thing going on with the hydroxide concentration and the pOH. If the pOH is 5, the hydroxide concentration is 1 times 10 to the negative 5th. If the hydroxide pOH is 11, the hydroxide concentration is 1 times 10 to the negative 11th. So there's definitely a pattern here. The other thing I want you to notice is if something has a hydrogen ion of 1 times 10 to the negative 14th, that's a very small number, then its OH concentration is 1 times 10 to the negative 0, or 1 molar. And so what is 14 and 0 add up to be? 14. Look at here. 13 and 1 is 14. 12 and 2 is 14. 11 and 3 is 14. So it turns out we've discovered a pattern. If you multiply the hydrogen ion concentration times the OH concentration, the hydroxide concentration, you'll always get the same number, 1 times 10 to the negative 14th. And we're going to use that to do some of our calculations. So let's look at this chart here. We're looking at the concentration in moles per liter. Another term for that would be molarity. And we're looking at both the hydronium ion concentration, that's the hydrogen ion concentration in water, and the hydroxide. And so this number here we have 10 to the negative 7th, negative 6th, negative 5th, negative 4th. This is 1 times 10 to the negative 3rd. And so that would give me a pH of 3. Look at this one here. Here the concentration of the H3O is 1 times 10 to the negative 7th. The pH is 7. What's it going to be on this last one? Negative 14, negative 13, negative 12, negative 11. And that's why this is pH negative 11. This is more basic, which says you have more hydroxide than you have H+. And the first example, you have more hydronium, let me say that correctly. Yeah, the hydronium ion, more H3O+ than OH. So whichever you have more of, hydronium or hydroxide determines if it's an acid, you have more hydrogen ion or hydronium. If it's a base, you have more hydroxide ion. If you have equal amounts of hydronium ion, H3O+, and hydroxide, it will have a pH of 7. Many students confuse those two terms, hydronium ion, H3O+, and hydroxide ion, OH1-. It's very important that you are clear in your mind which one I'm talking about when I use those terms. All right, let's see what happens here. So here's our pH equation. It's equal to the opposite log of H+. So I've commented on this graph one other time, but let's rediscuss it. So if we're looking at pH, pH is related to the hydrogen ion concentration and hydroxide. So if we can imagine, my right hand is the hydrogen ion concentration. So when we're looking right over here at this point, you have a very high hydrogen ion concentration and a very low OH concentration. So that means it's very acidic, so you have a very low number, like a pH of 1. And as we move from left to right, what happens is the numerical value of the pH goes up. Now we have over here, we have an OH concentration very high, and we have the H+ concentration up here very low. So if you have more hydroxide than hydrogen ion, it will be very basic, have a high numeric value, and that would be a number like 12 or 13. Now, this is a chart that is going to be very, very, very important for you to see how all these things are linked together. If you were in my class for stoichiometry, we had the mole island diagram, and that was our map, how we calculated from moles to liters to volume, and we navigated around. Well, this map is going to help us navigate between pH and POH and H3O+ and OH-. And of course, you can go from pH to hydroxide going this direction, or you can go down and over. Either way will work just fine. So let's look at these equations here and see what's going on. We have one that says that the pH plus the POH always add up to 14. And if you remember on our chart, I tried to point that out, that pH plus POH is always 14. Another relationship that I tried to show you was that H+ or hydronium ion times OH- will always equal 1 times 10 to the negative 14th. Those are very useful equations to memorize. Now, we've already met this one. If I know the hydrogen ion concentration, that's the H+, I can get the pH by taking the opposite log of that number. Likewise, if I know the hydroxide concentration, this shouldn't surprise you. If pH is the opposite log of H+, then POH is equal to the opposite log of OH-. So if I know the hydroxide concentration, I can take the opposite log of that and get to the POH. I'll show you how on your calculator we can go from pH to H3O plus, and how we can go from POH to OH concentration. This is merely a calculator activity, and we'll practice that here in just a bit. So let's pretend we're given the problem that we know something has a pH of 4.6, and we need to determine the hydronium ion concentration. First of all, what is the hydronium ion? Good. You said it's the H3O plus, and that's the same numeric value in terms of concentration as H plus. So the equation we would want to use to determine the hydronium ion might look like this. pH is equal to the opposite log of H plus. Now, I'm going to substitute in the pH that I know, the 4.6. So 4.6 is now equal to the opposite log of H plus. Now, to solve this, you want to multiply both sides by -1. That's easy to do. And now, the way we're going to get rid of the log is we're going to take the anti-log of both sides. Now, on your calculator, what this means is you use the second function and then hit the log button, log, not ln, and then hit -4.6. Now, on some of your calculators, this is the key that says 10 raised to some x power. So you're going to write 10 and then raise that to the power of -4.6 and hit equal. When you take the second log of this side, it gets rid of the log on this side. So we end up getting an answer. The hydrogen ion is 2.51 times 10 to the -5th molarity. Now, we know that's a pretty close number because remember I said pH always has to be close to the power of the hydrogen ion. If this were 1 times 10 to the something, then it would have been exactly a 4.6 of a whole number. But 4.6 is close to 5, so we know we've done it correctly. All right, let's try another one. And here's the beautiful thing. You can always check your answer by plugging in your value. If on your calculator you took your answer for the hydrogen ion, 2.51 times 10 to the -5th, substitute that back in for H plus, take the log of that and take the opposite of that, and voila, you get your answer back of 4.6. Now, depending on if you have a graphing calculator or a non-graphing calculator, a graphing calculator, you can literally type in opposite log, bracket, number, and bracket, hit equal. If you have a non-graphing calculator, the order of your keystrokes will be a little different. You'll have to type in the number, then hit the log button, log, and then take the opposite of that number to get back to your 4.6. You can do this. It's just going to require practice. So let's talk about how acids can dissociate. Monoprotic. What does the prefix mono mean? One. That's correct. And protic refers to one proton. So I'm going to give an example here of HA in solution. The H refers to a proton, and the A is the anion that it will make. So because this is monoprotic in solution, this will donate and make one proton and one anion. Some examples of monoprotic acids are hydrochloric and nitric acid. Now, if the monoprotic acid started off as a 0.03 molar solution, what would be the hydrogen ion concentration? If you think about stoichiometry, we use the coefficients. If there's a 1 here and a 1 here, they're going to be the same numbers. So the H plus is going to be 0.03 molar and the A minus is going to be 0.03 molar. Some students might think that the H plus will be 0.015 and the A minus will be 0.015 and you add the two up. That's simply not true. Whatever number goes here, we're going to use the stoichiometric coefficients to come up with the numbers below. Now, once we know the hydrogen ion concentration, we could certainly calculate the pH of that solution. So let's figure that out now. What would the pH be expected of a 0.03 molar hydrochloric acid solution? Well, picking the equation, pH is equal to opposite log of H plus, we substitute in the 0.03 molar, not the 0.03 molar here, but the 0.03 molar of the H plus, because pH is always a measure of the hydrogen ion concentration. At this point, it's a calculator exercise. So if you have a graphing calculator, opposite log, put the brackets, 0.03, close brackets, and hit an equal sign. And that corresponds to a pH of 1.52. Now, when we did our reactions of copper lab, we were using hydrochloric acid probably in a range of 12 molar, much, much more concentrated. And if you took the time to calculate it, you'll see it would actually have a negative pH value, the acid that we were using. What do you believe a diprotic acid is? Good. It deals with two protons. Can you give me an example? If a monoprotic is HA, what would a diprotic be? Say a little louder for me. Good. H2A. And when this dissociates, it's going to break into how many protons? 2. Good. Now, do I write that H with a subscript 2, or do I write that with a coefficient 2? Well, if you write it with a subscript 2, you're referring to hydrogen gas. That's not what we want. Instead, you want to write it with a coefficient of 2, and so we're going to write it 2H plus A 2 minus. Now, we have to understand that when we dissociate this diprotic acid, the molecule itself was neutral. So when it breaks apart, I have 2 positive ions and 1 negative anion of 2 negative. When you put the pieces back together, it is indeed neutral. Can you give me an example of a diprotic acid? I'll give you a hint. It's the most common acid sold in the world. Good. Sulfuric acid is correct. H2SO4. Now let's pretend we start with some 0.3 molar sulfuric acid. What would the hydrogen ion concentration be that it would produce, knowing that it's strong and will dissociate fully? Very good. If you said 0.6 molar, you're correct. What would the concentration of the anion be? 0.3 molar. You got it. Now, if I want to calculate the pH of this solution, am I going to put in there 0.3 molar, 0.6 molar, or 0.3 for the H plus? I hope you said the 0.6 molar, because that's the hydrogen ion concentration. So if I wanted to calculate the pH of a 0.3 molar sulfuric acid solution, it would be pH equal to the opposite log of 0.6 molar. When I type that in my calculator, I get a pH of a mere 0.22. That is more than 10 times more concentrated than a 0.03 molar hydrochloric acid. It's actually much more than that. Well, let's deal with a polyprotic acid. What does the prefix poly mean? Many. Good. So this is going to have more than 2 protons. So let me give you an example here, phosphoric acid. Now, phosphoric acid is a weak acid and doesn't dissociate fully generally, but for our problem, we're going to pretend that it does. So let's work backwards and say that we have a solution that's pH 2.1, and I want to find what was the original concentration of the phosphoric acid. So the first thing I must do is write the dissociation for phosphoric acid. Now, I've mentioned earlier that phosphoric acid is a weak acid and it doesn't dissociate fully. But for our first try at this problem, we're going to assume, it's not true, but we are going to assume 100% dissociation. So here's my phosphoric acid. It has 3 protons, so I'm going to make all 3 of those protons come off and be left with a phosphate. Okay? So from here, this problem looks a little bit different. It's a real head scratcher, isn't it? Because now we know the pH and we're trying to find the H3O+. So our strategy is going to have to be a little bit different here than what we did before. We're trying to find the molarity. We don't know the molarity of the H+, but we do know the pH. So let's go to a new sheet of paper. Here's what I think we should do. Let's write out the dissociation of phosphoric acid, assuming it gives 3 protons. Next, let's calculate the hydrogen ion concentration. If you go back to our little square sheet that showed us how to calculate pH to H+, what we remember is, well, this formula, pH is opposite log of H+. Well, this time, I know the pH is 2.1. I'm going to take the opposite log of both sides and multiply both sides by -1 and take the anti-log of both sides. On my calculator, that would be second log -2.1. When I do second log of log, that makes the log on the right cancel, and I'm left with the H+ concentration being 7.94 times 10 to the -3rd molarity. Now that is not the answer to the question, what is the phosphoric acid? Instead, I've only gotten the answer to the H+. Now the other way to do that calculation, this is a little ugly, is to use this side. H+ is 10 to the negative pH. So I take what is the H+ concentration? It's equal to 10 raised to the -2.1 power. And right away, I get the same answer, 0.00794 molarity, or 7.94 times 10 to the -3rd. I think most of you will prefer to solve that like I've done on the left side. Now, the step 3 here is to calculate the phosphoric acid concentration. What we did at this point was calculate the hydrogen ion concentration. We're trying to figure out the phosphoric acid concentration. How does the phosphoric acid concentration, right up here, relate to the hydrogen ion concentration? Unsure? Well, look at the coefficients. There's a 1 here and a 3 here. So every time you have one of these, you get 3 of these. Or for every 3 of these you get, this concentration should be 1/3 of that value. So we're paying attention to the 1 to 3 on the coefficients for the phosphoric acid and the hydrogen ion. So if we simply take our hydrogen ion concentration and divide by 3, we would get the apparent beginning concentration of the phosphoric acid, assuming 100% dissociation. That was a tough one. We'll have more practice for you to do on these pH calculations, and that will be what a lot of your homework time will be spent doing. And then feel free to email me, and I can help you walk through, maybe do some of the examples with you to help you with some of these pH calculations. Let's try one more calculation, and then we'll call it quits for today. So this question says, how many grams of magnesium hydroxide are needed to yield 500 mils of water with a pH of 10? Well, there's a lot going on in this question, and again, it looks a little different than what we did before. First of all, can we decide, is this an acid or a base, magnesium hydroxide? Okay, it's a base. How do you know? Okay, I heard one person say because it has a pH greater than 7. Yeah, I heard you over there. Yeah, somebody else said it's because it is a hydroxide, and hydroxides are basic. Both are good ways to figure that out. Well, I think because we need grams, there's going to be some stoichiometry involved here. We're going to also need a formula. So let's first write out the dissociation of magnesium hydroxide. Magnesium is an alkaline earth metal. All alkaline earth metals have a charge of 2+, and hydroxide is a 1-. So we can do the crisscross, bring the 2 down, the 1 down, and we'll get the correct formula for magnesium hydroxide, MgOH2. Now, I want to write out its dissociation. What will it break down to in solution? I hope you're going to tell me the magnesium and hydroxide ions, but how many of each do we get? We get 1 magnesium, and I hope you recognize you're going to get, because of that little subscript, 2 hydroxide ions. So now we've written out the dissociation for magnesium hydroxide. Looking at the problem, the only other thing I know right now is that it's going to have a pH of 10. Now I remember that pH is related to pOH, and pOH is related to OH. So we're going to have to do a little bit of work together on this problem. So let's calculate the pOH. Go back and look at your sheet. How does pH and pOH compare? Did you find it? pH plus pOH always equals 14. So if the pH is 10, the pOH must be 4. Good. Now we know the pOH. Now we can play that little game we did before to calculate the OH concentration. We could go pOH is opposite log of OH. We could, or, and this is much more direct, simply say the hydroxide concentration is 10 to the negative OH concentration. I'm going to do this second way first. It should actually, that's a typo, it should be OH concentration is equal to 10 to the negative pOH value. So if you put 10 and then you raise this to the negative fourth power, because that's the pOH, that's a typo there, apologize, you will get the hydroxide concentration to be 1 times 10 to the negative fourth molar. Now we can put that value in for the hydroxide concentration. Now, what we need is the original concentration of the magnesium hydroxide. Once we know its concentration and we know its volume, we can figure out its mass. So I want you to think with me for a second. It's a real chin scratcher for me. How do we go from OH to magnesium hydroxide? I think I have an idea. There's a coefficient 2 here and a 1 here. So the magnesium hydroxide concentration will be half of whatever the hydroxide concentration is. What's half of 1 times 10 to the negative fourth? And if you said 0.5 times 10 to the negative fourth, you're correct. Now, that might be correct. That's half, but that's not the right way to write in scientific notation this value. 0.5 times 10 to the negative fourth would properly be written 5 times 10 to the negative fifth molarity. Now we know the concentration. We're getting very close to getting this problem solved. Let's read the original question. It says, how many grams of magnesium hydroxide are needed to make 500 milliliters, that's a half a liter, of this solution? So I think our next step is to solve for moles. Do you remember this equation? Here's a blast from the past. Molarity is moles over liters. We know the molarity of our solution, 5 times 10 to the negative fifth, and we know the volume of our solution, 500 mils or 0.5 liters. So I'm going to go ahead and put that in. When I multiply molarity times volume, I'm going to be left with the number of moles. 2.5 times 10 to the negative fifth moles of magnesium hydroxide. I can almost taste this answer. We're getting really close now, almost done. I now have to go from moles to mass. So I need to figure out the molar mass of magnesium hydroxide. So I know that in magnesium hydroxide, I have 1 mole of magnesium that weighs 24 grams, 1 mole of oxygen, 2 moles of oxygen, each that weighs 16 is 32, plus 2 hydrogens each, that's 2 more grams. So 1 mole of magnesium hydroxide has a molar mass of 58 grams. Moles of magnesium hydroxide cancel, like that. And when I punch this in my calculator, I get an answer of 0.00145 grams of magnesium hydroxide would need to be dissolved in 500 milliliters of water, and theoretically, that should produce a pH of 10. Boy, that was a tough question. Will I ask you a question like that? Well, if we were in school, I definitely would. I'm not sure if I'll ask one quite that complicated for you, but it's a wonderful example of a problem to put together a lot of these things that we've been looking at. All right, we'll call that a wrap for today. You may need to go back and review and hit those slides and pause and listen real careful to how we did that problem. But that's a great example. Helps keep your brain sharp. All right, signing off for tonight. You guys have a good evening. And again, stay healthy.